Hello guys, welcome to tutorial 6 for CompSci 1MD3. And today the main topic is going to be recursion. And this is going to be a pretty important one because test 2 is coming up this weekend. And recursion is going to be something that you should definitely know for that. So we're going to be taking up some really good examples for understanding recursion. And feel free along the way, I'm going to be coding them. So if there's anything that you don't really fully understand about what's going on recursively with the functions, feel free to stop and ask some questions, and I can take anything up. So this is what we're going to be working with. We're going to be doing 3 main examples, and then after that we can do anything else you guys would like. But for now, let's take a look at what we're doing. So we have a binomial expansion, which I think you guys recognize, but if not, we'll take a look at that. We're going to be doing a sorting algorithm, which takes use of recursion, and it's going to be a very primitive one. And then we're going to be taking a look after that at a more advanced example of a sorting algorithm, which is actually used very much in the software industry and computer science, which is merge sort. And someone's asking if I can zoom in. Yeah, I can zoom in for sure. Hopefully that helps a little bit. And test 2 is due. I believe test 2, it's going to be the same format as I think test 2 starts, if I'm not mistaken, Saturday 9 a.m. and is due on Sunday at 9 a.m. So yeah, if I'm not mistaken, it is the 24 hours from Saturday to Sunday at 9 a.m. Yeah, but anyways, so this is going to be a simple recursive sort, and this is going to be a more advanced sorting algorithm which uses recursion and is very popular. So it's actually used by people in the industry, so that's important. Let's start off actually with this simple recursive sort because it's the simplest example of recursion that I have for you guys. So let's define it. We can say simple sort, and obviously it takes in some sort of array, or maybe I should call it a list, like L, capital L. Okay, and we want to think, well, how are we going to sort a list recursively? And I think you guys have covered recursion hopefully in class a little bit, but the idea is that you want to have a base case and a recursive step. And what I mean by that is you want to take your input and slowly boil it down to what you can consider is the simplest case of that problem, which you already know how to solve, right? And once that's done, you can do a recursive step. Now this is very popular in certain algorithms. For example, the Fibonacci sequence can be done very recursively because you know that if you boil it down to the first 2 elements of the Fibonacci sequence, it has to start somewhere. And it starts at 0, 1, for example, right? And then once you have that base case set down, you can build on incrementally from that and build on recursively. So what I mean by that is for future steps, you can just say that Fibonacci at I is equal to Fibonacci at I minus 1 plus Fibonacci at I minus 2. Basically, you're summing up the previous 2 elements to come up with the current element. So a similar thing can be done with sorting algorithms. And this is how we might do it. We might say, if the length of L is equal to 1, then we know it's already sorted, right? You cannot sort a single element list any further than it already is sorted. And we know that if it's not of length, if it's not of length 1, then we need to boil it down recursively. And the way we can do that is we can take the smallest element or the biggest element and put it where it needs to be. So for example, let's do something like this, right? We can say smallest is equal to min of L. As you guys know, the Python min function takes the minimum of a list numerically. And then once we've got the smallest, we want to remove it from our list and then sort that list. And then what we can do is if we have a sorted list and our smallest and they're separated, we can just tack on the smallest element at the front of the list, and then tack on the rest of the sorted list on the end of it. And so this is what I mean by this. We can say something like L.remove smallest, and then we can say return, or let's do this for clarity, right? We can say new list is equal to a list containing just that smallest plus a sorted list, which is what we have. So we can call simple sort on L here. And just so everybody knows, you can see that this is clearly a list, right? This is a list that contains one element, and this will also return a list because simple sort returns lists. That's the only type of element that we return, right? And so what happens here is that if we try and add two lists together, you get a list back. And so if I do smallest plus simple sort and this returns a list, then basically you end up getting something like this, right? Right, so this is the return value of this simple list. This is smallest. Basically adding two lists just combines the two lists and it'll put this one on the front of it. So just put that up here just so you guys know. And we can return that. Sorry. Yeah, we can return this. So that's pretty much it. You can see that we've covered our base case here, and we've covered our recursive step. So if we feed this a list, obviously it probably isn't going to start off at length 1, but what is going to happen is that in our recursive step, we're slowly going to get closer to the base case, which is the case in which we can just do something trivial, as in not use recursion, right? And once that's done, we'll pass in a list. It will slowly boil down by removing one element at a time until we get to the base case, and then it will come back up the recursion stack and add everything up that it needs to and satisfy all of these recursive calls. So I can show you how that might look with a test case. So let's, for example, say we have a sample list, and let's do some values like this, right? So this is clearly not a sorted list. And if we pass this list into our new function that we've just defined, our sorting algorithm, we can run it and take a look. And you can see that our function actually sorts it properly, which is great. So this is a really pretty simple example of recursion. And everything is going to build off of this idea that I'm sure you guys have covered in class regarding Fibonacci and I'm sure some other applications of recursion as well. But hopefully everybody sees what's going on here, right? Does anybody have any questions about this sorting algorithm or how it works? I'm going to just wait for like a minute or so, maybe a little bit less, because I do want to make sure that everybody understands this, because it's going to get a little bit more complicated, so I want to understand that you guys know the recursion. Okay, in the meantime, I'm going to start laying out the next question, and if we get any questions in that time, I'll take them up. But the next thing we're going to do, let me actually reorder this. Right, and so now we have our recursive sort, which we did here, and we're going to do binomial expansion as our next one. So we have a question. Lacey's asking if recursion will sort a list. Recursion is not necessarily used to sort a list, but it can be used to sort a list. Recursion is a general technique in programming where you call the function within its own function definition. So you can see here, and this is not a common thing, right? It's only used when recursion is used. So in our function definition for simple sort, we end up calling simple sort, right? So basically, when you call this, this will run. But when this runs, you will call this again, which will run this, which will call this again, which will run this. So you kind of get into this like infinite recursion loop thing going on, which is why you need to have a base case so that it doesn't go on forever, right? Here, we're being very careful to slowly direct our list towards the base case. Every single time we make a recursive call and call this function, our list slowly gets smaller, right? Because we're removing from it until it eventually becomes of length 1. And then this base case is returned. And so in this case, we don't make another recursive call. We instead just return L, which means that the deepest call of this function can be resolved, and it will just be L. And so we'll be adding L to a bunch of other calls, right? So to answer the question, yes, recursion can sort a list, but it can also be used for many other things other than sorting, such as Fibonacci. And yeah, it's simply just a technique where you call a function within its function definition. Cool? That's great. Okay, so here we're going to do something cool, which is binomial expansion. And I'm sure you guys have taken math, especially if you've taken like high school stats or I guess it's data management in Ontario. And basically, just in case anyone's not familiar with it, this is kind of the idea of binomial expansion. It's a mathematical idea, and you might have heard this referred to as Pascal's triangle. It's basically the same thing. And binomial expansion is exactly what it sounds like. It's when you take a binomial, such as a plus b, and you expand it for its different powers. So as you know, a plus b to the 0 is just 1. A plus b to the 1 is just a plus b. A plus b squared, and this is where we start expanding, right? We go a squared plus 2ab plus b squared. And the same thing continues. So if you abstract away these constants and you just take a look at the numbers, we get Pascal's triangle, right? Which is this whole thing. And keep in mind, this is the exact same coefficients as these numbers. So we've just taken away the actual variables and left in the coefficients. And this is what we're going to try and replicate in Python. We're going to try and come up with a recursive function that is going to give us the coefficients for a specific value of n. So you saw that this is the coefficients for n equals 0, right? A plus b to the 0, you just get 1. A plus b to the 1, you get 1 and 1. So what our function is going to do is it's going to take in a number as input, and that's going to be basically the row number, right? It's the value of the exponent, and we're going to return a list of these numbers. So if you gave the function of input of 3, right? That's a cubic binomial expansion. We're raising it to the cube, and so we're going to spit out a list 1, 3, 3, 1. That's going to be our Python return list. Cool. And so you might think, okay, how are we going to code this in Python? And especially if you think about it recursively, you're going to think about how can I use the previous one, the previous row, to build my current row. So obviously, the first row doesn't have a previous row, which should like ring the bells in your head that we're going to be using this as the base case, because this cannot even refer to anything behind it. It is the lowest case. And we're going to hard code that into our code. We're going to say, if n is equal to 0, our list is just going to be a list containing 1, right? And then if we try and return the list for a value of n equals 1, right? Then we're going to be using the previous list to calculate that. So if we call binomial expansion of n equals 2, to calculate n equals 2, we're going to use n equals 1. And to calculate that n equals 1, we're going to calculate n equals 0, which is up here. So we can start coding this up. Let's say, for example, our base case is going to be that if n is equal to 0, right, we're going to return a list which contains just 1. Remember, we said we're going to hard code that because that's our base case, right? And then everything else is going to be based on that base case. Now, we could say else here, but notice that we actually don't need to, because if this is actually true, then our function will return here, which means that as soon as it returns, it will terminate that function call, which means it won't even go down to read what's below it. So we actually don't need this else here because it's kind of redundant. Basically, if it makes it to this part of the code, like down here, then we already know that this isn't true because it would have returned by then, right? So here, we're going to take care of the case where n is not equal to 0. And the way we're going to use that is by using the previous row. So to calculate a non-base case output for binomial expansion, we need to use the previous output of n minus 1, right? So we can say something like this. The previous output is equal to binomial expansion of n minus 1, right? Now we have that, and we can work with it. So the question is, what are we going to do with our previous binomial expansion? And if we take a look back at the triangle, we can try and examine it and analyze it to see how we can come up with an algorithm. For example, let's take this one, right? 1, 2, 1. If we were asked to find the binomial expansion of n equals 2, which is this one, how could we get it from the previous one? Well, if you look at the whole triangle, you would notice a pattern, which is that 1, 2, 1 is basically 1, and then 1 plus 1, which is 2, and then that 1. So there's always 1s on the left and right side, right? However, the middle is composed of summing up the inner elements, right? So let's try and extrapolate or bring that idea to n equals 3 for the cubic. We have our 1 that's on the left side. How do we get this 3? Well, this 3 is just 2 plus 1. We have another 3, which is the 2 plus 1 over here. And then we have our terminal 1 here right at the end. And the same thing applies in the rest of it. 1, 3 plus 1 is 4, 3 plus 3 is 6, 3 plus 1 is 4 again, and then we have our ending 1 on the right here. So we kind of know what we have to do. We just have to sum up everything in the middle and enclose it in 1s, right? So how would we go about doing that? Let's take a look. So let's define our output list, which is going to be a list. And we know that it's going to be equal to 1, right? So how are we going to do that? Just like this. And we're going to need to add on everything else. So we could do something like this. We can say for I in range of 1 all the way to n minus 1, right? And I'll explain this if anybody doesn't get it, but we're going to be appending the sum of the previous two elements in the last expansion output. So it's going to be something like this, right? At I plus previous at I plus 1. And after we've done that, we're going to have all of our inners, and at the end, we can just slap on our remaining 1, right? Just like that. So keep in mind that this is basically the same as doing this, right? Instead of initializing a list as just containing 1, we could just initialize it empty and then append 1, just like that. And now it looks a bit more symmetrical, right? So let's take a look at what's going on in this for loop, just in case anybody doesn't understand it. We know that we don't need to start at 0 because actually let's take a look at this for so let's say we're trying to calculate n equals 3, right? So our previous is going to be for n equals 2, which is 1, 2, 1, right? Okay, so how are we going to build that? Well, we're basically just going to have this 2 plus 1, which is 3, because we're going to start at I equals 1, which is the second element in a list, right? I equals 1 over here, and it's going to be I plus 1. So it's going to be this plus this, which is 3, right? And we're going to add that on, and that's it. It'll be added on, and then we just have to add our terminal 1, and we're done. And so we can return our output after this, right? We could just say return output, and that's all we got to do. So if we try this with a test case, for example, we can say, let's try and print the binomial expansion of, let's say, 3, which is exactly what we tried to find, right? It should be 1, 3, 3, 1. We get an index error. Okay. Ooh. Yeah, so we're trying to go up to n minus 1, adding previous at I plus 1. So that's going a little bit out of bounds. And here's how we can solve that. Just give me one sec. So actually, instead of doing what we did here, we can actually start this at 0. And if we go up to n minus 1 and add I plus 1, this will terminate. So for example, if our list is 3, it'll terminate right before the final thing. So this should still give us a correct answer. And yeah, we were basically going a bit too far. By starting at 1, we were we were actually ignoring the exclusivity of the final parameter in the range function, which is not good. But this works just as well. And if you're wondering why that still works, even though I moved it from 1 to 0, and you can see that it works for all the values. The reason it still works is because, as I was showing you here, if we start like this and just add 2 plus 1 here, it's actually the same as adding 1 plus 2 here. And in the same way, if you try to add 3 plus 1 here, it's the same as adding 1 plus 3 here. Which is why it doesn't really matter if we start at 0 or if we start at 1. But for the sake of keeping our index in bounds, we will use 0. So that's another example of recursion for a pretty cool application, which is mathematical. And we can actually test our boundary cases, like for example 0, and we'll see that it gives us our correct value, which is the top value of the Pascal's triangle, right, for an exponent of 0, an exponent of 1, so on, so forth. And you can see that if we actually go for I in range, let's say 6, for example, if we print out the binomial expansion of I, it's not exactly a pyramid or a triangle because of the way Python's formatting, but you can kind of see how the triangle is almost there. It's there by value, it's just not there by shape. Cool. That's this whole function. So the most important part is that you understand how this recursion is happening here. If anybody doesn't understand why this recursion is happening or how it's happening, right? We're calling binomial expansion inside of binomial expansion's function definition. If anybody doesn't get that, please stop me and let me know. Right? But basically, we keep on calling it until we hit our base case, which is something that we've had present in all of our recursive problems, because it's a necessity in recursive problems. Otherwise, they'll just keep on recurring forever. This function will never end. Can you go over it one more time? Yeah, for sure. We actually do have a decent amount of time, so it won't be too bad. Basically, we are trying to use the previous output to form our current output in the triangle, right? We make a base case so that our recursion doesn't go on forever. We say if n is equal to 0, return just a list of 1. So if we give it n equals 0, right, if we call it for n equals 0, we're just going to get 1. But if we call it for an n which is not 0, let's say we try and call our binomial expansion function, and we pass in an n of 1. This is not going to execute because n is not equal to 0, so we're going to hit this line of code. And it's going to say, let's call binomial expansion on n minus 1 and store it as the previous output, right? Well, what is n minus 1? We're calling it on n equals 1. So n minus 1 is 0. So this function call is going to go back and it's going to run all of this function again. But this time, n is equal to 0. So that function call is just going to return a list of containing 1, right? So in previous, this variable is going to be storing a list containing just 1, and our function is going to continue as normal, right? So we can examine what it's going to do in this case. We're going to create a list, which is our output. Notice how we are manually appending our 1s on the beginning and on the end of the row, which, as you can tell, is the case for all of the rows. So that's something that we can do every time. But in the middle, for like the meat of the sandwich of the row, right, we need to sum up the inner elements. So to do that, we can loop through the elements by going from 0 to n minus 1 exclusive, which, you know, for the case of 1, that's just 0. So it's not going to add anything. This is just going to be an empty loop, and it's going to add 1. It's not going to do anything here, and it's going to add 1 again, which is why our output for n equals 1 is just 1, 1. But for example, with 1, 2, 1, if we called this function with n equals 2, well, this isn't going to run. This is going to run on n minus 1. It's going to do exactly what we just said, right? It's going to do that whole process, get n minus 1, it's going to store it here, right? So you can see that when we call this function with n minus 2, n equals 2, it has to find the value of binomial expansion at n equals 1. And in order to do that, it has to find the value of binomial expansion at n equals 0. So when n is equal to 2, Python is kind of stuck here until it actually finds the value of binomial expansion at n equals 1. And when n equals 1, and it's running this function, it's stuck here until it finds n equals 0, which is instant because it just returns. So you can kind of see how we're like going down the recursion and then back up the recursion, right? The way that kind of happens is that for binomial expansion, I really want you guys to understand this concept, right? For example 2 is going to be binomial expansion 2 prev equals binomial expansion of 1, which is going to hit prev equals binomial expansion of 0. And we're going to be done, we're going to done calculating binomial expansion 1. And similarly, we're going to be done calculating binomial expansion 2. So do you kind of see how this is going? Like it's like we're trying to find expansion 1. In order to do that, we call expansion 1. In order to do that, we call expansion on 0. Now we're done, so we can finish doing the rest of this function, which is basically all of this down here. And once we're done that, we can finish with this. Because as soon as we run this line, previous equals binomial expansion at 1, we are stuck here waiting all the way until this happens. So we're stuck here waiting for this and this to finish. And only then we are done calculating binomial expansion of n minus 1, which is for n equals 1. We store it in here and we can calculate the rest of it to find binomial expansion of n equals 2. So hopefully that makes sense. And if not, like, feel free to ask me about it later on. For the sake of time, we do need to move on because merge sort is probably our biggest, well, it definitely is our biggest function. And it's also the most complicated example of recursion we're going to do. But I'm sure you guys can understand it. So we are going to define our merge sort function just like that. And this is going to take in some sort of list. Now, I could call it L here, but the thing is, the way merge sort works is that we actually split the list up into two halves, a left half and a right half. And so I actually want to be able to use capital L to represent the left half of my list. So I'm actually not going to call the input L. I'm going to call the input variable R for array, right? An array is basically a list. And before I start coding this, I want to show you guys a quick example of merge sort. So I've pulled up here a YouTube video, which is just quickly going to show you guys what's going to happen. Before I press play, I just want to warn you guys, or not warn you, but just give you a heads up on what is going to happen briefly. And that's basically, you can see here we have an unsorted list. Our objective is to sort this list. And the way we're going to do that is by breaking it down into halves as best as we can. Obviously, this is an odd number of elements, so we can't break it evenly into halves because it's not divisible by 2 evenly. But we can do our best, which means we're basically going to split it into 3 and 4 or 4 and 3. And we're going to keep on splitting it until we get the smallest possible pair of elements. And then we're going to start sorting those independently, right? We're going to sort each pair of elements. And then once each pair of elements has been sorted, we're going to merge them back together. And since our sublists are already sorted when we merge them, we can actually do it. We can do that merging process linearly. Basically what I mean by that is we only have to examine every element of the list once for every merge that we do. And maybe this video will explain it a little bit. You can ignore this this white text. I just want to show you guys visually what's going on. So you can see that we split the list in halves as best as we can. And we're going to keep on splitting until we've boiled it down to our smallest possible subdivisions, which here are just pairs. And then we boil it down further to just single elements. And then we are going to start sorting. So you can see here, what they've done is after they had it in single elements, they sorted each sublist. they didn't sort the whole array, but they sorted the smallest possible pair of elements, which is just a pair of two elements, right? So 3827 got sorted to 2738. 43 and 3 got sorted to 3 and 43. 9 and 82 was already sorted, so we didn't have to do anything to sort it. And 10 is just an element on its own, so it's already sorted by definition, right? And now that we've sorted all of our sublists to the best of our ability, we're going to start the merge, which is why it's called merge sort, right? Now we have all of these sublists, right? They're all small pieces of our total list, and we're going to start merging them because they're already all sorted. So you can see first what we're going to do is we have these two sublists, right? 2738 and 343. So we're going to merge them by comparing each of their lists individually. So we'll have 2738. We start by looking at the first element in each sublist. So we compare 27 to 3. Which one is smallest? 3. So 3 goes first. Since we've already put 3 down, we move what we're examining over by 1 in that sublist. But since 27 was not picked, we're still looking at 27. So now, instead of comparing 27 and 3, we've already put 3 on. We compare 27 and 43. 27 is a smaller one, so we put it in. And since 27 was picked, we advance our pointer, which is what we're using to keep track of what we're examining, right, in the sublist. We're going to move it over to 38, compare 38 and 43. Obviously 38 is smaller, goes first, and that leaves the remaining 43 to go in. We do the same process for these sublists over here, which is 9, 82, and 10. And let me just rewind a little bit. You can see that we started off at the first element of each of the two sublists, right? 9 and 10, which one's smaller? 9. We pick 9, so we advance our pointer to 82. 10 is smaller than 82, so it goes first, and then 82. And now we merge again, right? So now we're doing the same thing, but this time on these two sublists that were created from even smaller sublists. So yeah, you can see it's the exact same process. We started at 3 and 9, and we started moving on our pointer as we needed to. And there we go. You can see that this right here is our final answer, and it's basically a completely sorted list of what we got initially, right? And I will tell you guys, this is a more complicated method of recursion, and it's probably complicated enough that you aren't going to get something as hard as this to code for, say, on a midterm or a test. It's probably going to be something a bit easier. But nevertheless, it's a good exercise to go through, and I do want to code it live for you guys just so you can see how it's kind of constructed. And as you can see in the video, it has a very cool method. And what you guys should be recognizing is the fact that this sorting algorithm is done recursively. You could see that we kept on splitting until we hit some sort of base case. Now, what was the base case in this scenario? The base case was that the length of the array was sufficiently small enough that it's like we can't split it up anymore, right? And that's kind of what we're going to be doing in our function. We're going to be using a base case. And then we're going to be climbing back up the recursion stack, which is kind of what I showed you with this right here. We're going to be climbing back up, and we're going to be merging as we climb back up. So we're going to merge, which is going to give us our sorted sublists, and we're going to merge again, which is going to sort those sublists, and then we're going to merge again, and that's going to give us our final fully sorted initial array. So let's start. I'm going to use while loops for this one, just as a heads up, instead of for loops. And the reason I'm doing this is because, as you could see in this in the video that we looked at, this idea of keeping pointers of where we're currently examining is actually a lot more intuitive to do with while loops, because we can control our pointers very explicitly. If we want to advance a certain pointer, we can just increment the value of that pointer. Say I or j or k might represent the position in the list that we're looking at. So that's a little bit easier to understand, in my opinion. So that's what we're going to do. And actually, what we're going to do is, instead of creating a function that returns a sorted list, we're actually going to create a function that sorts your list on the spot for you. So instead of a return value, it just actually sorts your list. So let's try that out. We're going to say if the length of this array is greater to 1, then we're going to find what the middle is going to be. And you guys can see that in our video, they kind of found the middle to be right around here. They use this formula here, which is L plus R over 1. We can do something similar, which is just basically we're going to be integer dividing by 2, right? So we're going to say the midpoint is going to be that length of the array, integer divided by 2. And now we're going to create our initial subhalves, right? So this is what I was talking about earlier for you guys, about why I didn't want to use L and R. For L, we're going to say it's the left subhalf, which is going to exclude the midpoint, and our right subhalf is going to include the midpoint. Obviously, that doesn't matter which half includes or excludes your midpoint, but it just makes it so that I can do something like this, right? I can splice our list by saying array from the beginning all the way up to but not including the midpoint, and then I can say that our right side of the array is our array sliced up from the midpoint and including it all the way to the end. And this is some very beautiful symmetric Python code, thanks to slicing. And now we have our two subhalves. So what are we going to do with our two subhalves? Well, we got to split them up again, right? But that's the thing. That's the recursive step. So instead of manually splitting up, because we don't know how many times we're going to have to split it up, we can call merge sort on those two arrays. Just like that. Oops. So what do we do after this? Well, now actually we have to take care of the actual sorting. So, or I should say the merging. So we're gonna have a while loop, which says that while I is less than the length of L, and J is less than the length of the right half, we're going to merge. But first, we need to obviously initialize our variables, just like that. Oh, and actually, we're going to need to use something to reference our array itself. So we're going to have k here, and that's also going to be 0 to start off. And don't worry if you don't exactly know what's going on just yet. I think it'll all become a little bit more clear once I code this and you see where the idea is coming from. We can say here that if L at I is less than R at J, right? That's kind of what we were doing in the video, if you noticed. Then the array at K is going to be equal to, can you guys guess it? It's going to be equal to L at I, right? And if this is not true, then it's obviously going to be the other one. So we're going to have array at K is going to be equal to R at J, right? So keep in mind that I is the pointer that we're using to point to which side of the left subarray we're currently looking at, right? So I here would be 1, because here's 0, 1, 2, 3. I is 1, J is 1 as well, because they're both pointing to the index 1 of their respective subarrays, right? And so if L at I, which is the value at that position on the left side, is less than R at J, which is the value of the element on the right side, which is being currently pointed to, then we're going to store, or we're going to rewrite that position in our array as that variable. That's right. So basically, we're going to have to increment I here because we obviously, every time we use the one that we were looking at, we need to increment the pointer so that we can look at the next one. And similarly, if we actually choose R at j, which is the element on the right side, we need to increment j so that we look at the next one on the right side. And regardless of which one we pick, we need to increment k, because obviously if we end up picking one, like picking one of these two values and storing it at array at k, the next time around we don't want to store a new value at the same thing. We want to store it at the index that's one over to the right, so that we keep on moving and advancing and adding new elements to our array. And so that takes care of the main merge, right? Now there is one small caveat, which is what if our two initial sublists are not actually evenly split, or any sublists are not actually evenly split for that matter. If any sublists are not evenly split, and this while loop only goes on as long as I is less than length of L and j is less than length of R, then that means that as soon as we're done, basically as soon as I has sufficiently gone through a whole subhalf, this while loop is going to terminate. But we're still going to have elements in the right subhalf, for example, that have not been added onto our array. So now we need to add functionality to make sure that that happens. So just in case after this while loop is done, just in case there's still elements on the left subhalf or on the right subhalf that needed to be added to the array still, we need to do that, right? And the only reason we can't do it inside this while loop is because we need to be able to compare a value from the left subhalf and a value from the right subhalf. But obviously, if one is longer than the other, then we cannot do that. So after we're done going through the same length for both subhalves, we're going to make sure that we clean up any of the remaining ones on the left subhalf if they exist. So we're simply just going to, basically, we know that if the left subhalf is already sorted, right, which we can assume it is because of the recursion, then we know that all we have to do is just add on each of those elements onto the array, right? So L at I is just going to go to RK. We just increment I, we increment K, and simple as that. And that's going to keep happening until we've gone through all of L, if there's any left over. Similarly, what if there's some left over in R? We need to cover that case too. Obviously, these two are never going to be true at the same time. It's always going to be one or the other. But you can see how this works, right? If this had no leftover elements, then I would already be equal to length of L, which means that this would never run. But if there were some leftover in R, then this would run, and vice versa, right? It could be switched around. Here we just say R at j, and instead of I going up by 1, j goes up by 1, and k also goes up by 1. And that's actually our whole algorithm. And this is a really beautiful algorithm thanks to the recursion. I'll try and demonstrate an example. We're almost out of time, but shouldn't be an issue. Let's say, for example, we have the same sample array that we were using up here for a simple sort. Let's just copy that. We can call, since merge sort doesn't actually return anything, it sorts your algorithm in place. It sorts your list in place. All we have to do is actually call merge sort on our sample list, and it will actually modify sample list. It will modify that list. So now we can just print it again afterwards, and it will have been changed. And there you go. Beautifully, it prints 1, 1, 2, 3, 4, 5, 7, 8, 9, which is perfectly sorted. So I'm going to save this, and I'm going to put this up on Avenue, just in case you guys want to play around with it. If you guys don't completely understand any of it, and you want to fiddle around with it, I would strongly recommend putting print statements in like different spots of this algorithm and seeing how it works, right? You can, if we do something like this, print L, print R, and just some sort of divider, like that, you can see that now we're starting to get some output. That when we initially split up this list, it splits it in 2 halves, like this, and this is our left subhalf, this is our right subhalf. And then the next call, recursively, it splits it up into 2 halves again, so now we're splitting this up into halves. And it goes 4, 2, 5, 3. And now we split this up into halves, 4, 2, right? And then we got to split this up into halves, which is 5, 3, right? And then we got to do the same thing for the rest of it. And it gets sorted right here. Simply by just putting them in place one by one, we just merge them and we put them in place right back into our array, just like that. Now, if we didn't want to make this an in-place algorithm and we instead wanted to return a new sorted list and not modify our original list, if we wanted to leave our original list unchanged, we could simply just define a new list here. Instead of using the original input and modifying that, like this, we could just define a new one by saying like output, right? And we'd need a helper function for that, but it wouldn't be too bad. And so yeah, we would have a second function that just basically defines an empty list and starts passing it in, and every time you need to update something, you just throw it into the list, and then at the end of the whole function, you can just return that new output list, and it will sort, or it will have all the list as a sorted list. So if anybody has questions regarding this merge sort algorithm or anything else that we've done today, feel free to ask, and I'll stick around for a few minutes to try and answer them if you have any questions, and if not, then best of luck on test 2, which is this weekend, and I'll see you guys next tutorial. Yeah, you can ask a question about the assignment. You can go for it. No problem, Ivan. For A4Q2, I made the string lowercase. Okay, actually, let me take a look at Q2 because I actually do forget a little bit what the questions are. Give me 1 sec. I made the string lowercase and turned it into a list, then made that a set. But everything in the set, so it's not like the original string. Do you think that's okay? Okay, so I'm assuming question 4 is the one about, wait, now I'm a little bit, oh, A4Q2. I was looking at A4Q4, oops. Yeah, that's totally fine. Thank you for asking because it's not always fine. In this case specifically, you will not be capitalized because everything is lowercase, right? So we did say that that hello is equivalent to hello. So if capital hello is equivalent to lowercase hello, we definitely are not going to dock you marks for if your set is the exact set that it should be, except some of the words are capitalized or lowercase when they should be the other, or vice versa, right? It's not going to matter because we're ignoring all capitalization in this question. So yeah, I think you're fine. Any other questions? Awesome, no problem. Have a good weekend, guys, and best of luck on the midterm. I will throw this up on Avenue so you guys can check it out later. Goodbye.